Hello everyone, welcome to my channel Essentials of Electronics. In today's video, we are going to discuss some waveform generating circuits using op-amp, waveform generators using operational amplifiers. The first one I am going to discuss here is a square waveform generator. Yes, I'll draw the circuit diagram of a square waveform generator, an op-amp, inverting and non-inverting terminal, a capacitor connected to the inverting terminal, resistor in the feedback. Yes, a biasing network with two resistors R1, R2, V0, feedback resistor, and a capacitor. So here with the proper designing of suitable values of resistors, capacitors, and the biasing resistors R1 and R2. As soon as the supply volt VCC is given, the square waveform generator generates a square waveform, and the maximum value of which is plus VCC and the minimum value of minus VCC is obtained. The current flow is from the output towards this V naught is equal to plus VCC, charging the capacitor positively. This point charging is theta into VCC, at which the comparator action will flip the output to minus VCC. The values of the resistors and the capacitor determine the rate of discharge, and therefore it's called the period. This point is the point at lambda VCC. Therefore, this value of lambda from the voltage divider is R1 divided by R1 plus R2. When V1 reaches at lambda VCC, then the switch to minus VCC at the output occurs. The capacitor has charged to plus lambda VCC and now begins to discharge. The general charging equation for a capacitor, which already has the original charge value of Q is equal to Cv into 1 minus e to the power of minus t by Rc plus Q naught into e to the power of minus t by Rc. For this case, V is equal to minus VCC and Q naught is equal to lambda C into VCC. So the charging equation is Q is equal to minus C into VCC into 1 minus e to the power of minus t by Rc plus lambda into C into VCC into e to the power of minus t by Rc. Now when the charge gets a value of minus lambda VCC, another switching state will occur. This time is half the period of the square wave, so it will be represented by t by 2. At this time, minus lambda C of VCC is equal to minus C into VCC into 1 minus e to the power of minus t by 2 Rc plus lambda into CVCC into e to the power of minus t by Rc. So thereby we will be getting T is equal to 2 times of Rc ln of 1 plus lambda divided by 1 minus lambda. Then V reference value will be equal to beta, the feedback ratio of the R1 and R2 resistors, and beta is equal to R2 divided by R1 plus R2. When V naught is initially at plus V sat, the capacitor charges through R2 plus beta V sat. Then V naught goes to minus V sat. That is initially it is at V naught is equal to plus V sat. Capacitor charges to R2 plus beta V sat. Then V naught will be going to minus V sat. This was again from minus V sat to plus V sat, the capacitor discharges and then the cycle repeats like this. Thus, a square wave is generated between the two limits plus V sat to minus V sat. And this amplitude is decided by the values of the resistors connected and the feedback ratio beta. This is about square wave generator circuit. The next circuit we are going to discuss is triangular or rectangular waveform generators. So first I will draw a simple circuit which we are familiar with. Simple circuit in which a closed loop is maintained. This resistor, we have two operational amplifiers in this circuit. Yes, capacitor in the feedback path and V naught. So I will name the value components. Two amplifiers A1, A2. Let the connecting resistor be R1, R2, and a variable potentiometer R3. As soon as the potential divider sets its network, the first operational amplifier generates a waveform which will be acting as a square waveform, and this square waveform is fed as input to the second operational amplifier A1. We have connected a capacitor in the feedback path which will charge and discharge according to the positive and the negative input given to the second operational amplifier, and hence a triangular waveform is generated. So the output of this trigger circuit will be a square waveform, and when this square waveform is given to the input according to the charging and discharging operation of the circuit, uh, triangular waveform is generated. Let the output of the Smith trigger plus V sat. This forces the current plus V sat divided by R1 through the capacitor. The charging of the capacitor C1 with polarity positive to left and negative to right. This produces negative going ramp at its output for the time interval T1 to T2. Now the direction of the current through the capacitor reverses. I will draw the waveform of the both the plus VSAT to minus VSAT. This is the output of operational amplifier 1, which is acting as a Smith trigger. With the help of the reference voltage, it will be able to generate a square wave. And this output is fed to the second operational amplifier, and the capacitor, as it receives plus VSAT, It is already at a plus VCC value. It will start to discharge and then charging and discharging. Thus, a triangular waveform is obtained at the output of amplifier 2. And these values will be varying from plus VRAM to minus VRAM. So the square waveform oscillates from plus VSAT to minus VSAT. Triangular waveform oscillates from plus or minus VRAM. We will try to obtain the output voltage ratios of the circuit. Let V naught dash be the output of the first operational amplifier. That divided by R3 is equal to V naught divided by R2. And V naught dash is equal to plus VSAT. V naught dash is equal to plus VSAT and V naught is equal to minus VSAT. Plus VSAT and minus VSAT are equal. Plus VSAT and minus VRAMP are plus VRAMP and minus VRAMP are equal. Therefore, VSAT by R3 is equal to VRAMP by R2. Therefore, the triangular VRAMP value depends on the biasing resistors connected into the saturation value of the peak to peak voltage of the VRAMP is equal to 2 times of R2 by R3 into VSAT. The input voltage and the VSAT are equal, then V naught peak to peak value of voltage is equal to minus 1 by R1 C1 integral of 0 to T by 2 into minus VSAT dt, which is equal to VSAT by R1 C1 into T by 2. Therefore, the total time period generated is equal to 2 times of V naught peak to peak into R1 C1 divided by VSAT. We know F is equal to 1 by T, therefore the output frequency of the circuit is R3 divided by 4 R1 R2 into C1. This is a frequency which is generated by the at, at the output of the operational amplifier 2. Thank you.